Just as a level set, I joined Microsoft about 9 months ago. Prior to that, I was CEO at Cycle Computing, and we helped people run a really large amount of compute across internal and external infrastructure. And so in joining Microsoft, there's been a lot of eye-opening. It's great to be behind the curtain on a cloud provider. And what I'm here to talk to you about today is a continuation of the work we did at Cycle in helping companies that used EDA design both on-prem and in cloud, as well as talk to you about some of the special stuff that Azure does that's pretty unique relative to these workloads. So I'm hoping to educate you on both of those fronts. We're going to have about 15 minutes for Q&A at the end, so if you have any questions, please just hold them or raise your hand if it's really important, and I'll happily deal with it at that time. So in terms of silicon development flow, I think we all know that there are multiple stages in this process. There's generally different categories of work, whether it's from design or place and route and tape out, all the way through newer processes that are on the IoT spectrum. All of those processes require slightly different infrastructure in order to execute them well. And so on early stage design, it's actually not the same, but similar to a number of constructs that we have in software development. And even Microsoft designs HoloLenses and Xboxes and so on and so forth. So we actually have clusters dedicated to running a lot of these workloads in-house. The challenge is that the needs for faster time to market, correspondingly faster time to result, and the ability to be able to run various parts of this design flow quickly and easily in case you need to do a re-verification, for example, is increasingly hard. Not only that, the designs themselves are actually requiring more memory and more compute power, so they're on an exponential basis. As we all know, like a 7 nanometer process, you now need about 4 terabytes of RAM on an individual server. These requirements are also not going to go away. So from a hardware vantage point, having a fixed infrastructure that you buy and use over a 3 or 4 year time frame gets more challenging as the processes that you're using to create the chips have increasing requirements for both RAM and compute as well. And this creates a flexibility problem. So what I'm going to talk about today are a number of different topics, and I just wanted to establish this up front. We're going to both cover kind of the different aspects of customized hardware that you need to have for various parts of EDA design. The second thing that we're going to also be able to deal with is how do we think about utilization? So most clusters on-prem, as opposed to a web environment that's 20 to 40% utilized. I ran a Disney movie production that had a compute render farm that was 90 to 95% utilized. When you have expensive licenses like people in this industry do, you're even higher utilizations. How do you think about utilization and manage clusters on demand in cloud? How do you think about blob versus NFS POSIX file system global namespaces and be able to actually support them and enhance them when you run externally in cloud? There's also a number of different schedulers in this space, but LSF and UGE are probably the two most common. We'll talk a little bit about creating those environments and supporting them over time, as well as how we deal with kind of the engineering and governance and cooperation sides of running these workloads, both on-prem and external. So these are the set of topics that we will cover today. The reason why I'm at Microsoft, and we actually had the option to go to a number of different cloud providers, but I think the critical part for us was that Microsoft's philosophy best aligned with what we saw at Cycle when we were running workloads for customers. Number one, obviously productivity is the primary benefit of cloud, but I think the real key is hybrid. Microsoft has a key focus on enabling people to be able to use both their on-prem infrastructure to extend cloud capabilities on-prem through things like Azure Stack, and be able to run those workloads externally when it's appropriate or when it's beneficial. For example, a re-verification of a design. And do that in an intelligent way and in an environment where it's trusted. So we have workloads that are running, rocket design, both to carry probes to Mars, but also for military purposes on government cloud. And we've met more certifications than any other provider in more jurisdictions to enable those workloads to run in a trusted way. And this is a critical component of our decision to come to Microsoft. We ran a lot of Global 2000 workloads that were sensitive sensitive in nature, and the Azure cloud is focused very heavily on enabling this philosophically. In particular, there's a focus on global scale, which is having data centers that are low latency access to wherever your design engineers are, and this is particularly important for FlexLM servers or VDI sessions. We also have focused holistically around security and trust. High performance compute and storage is an area that I now own various aspects of the H infrastructure that Azure provides that has full InfiniBand capabilities. We have uniquely differentiated hardware that makes it very easy to run large-scale workloads in a highly cost-performant way. And then, in addition, there's a company-wide focus on IoT and AI. And we can talk about that a little bit after the session. I'm not going to cover that in particular at this session today. So relative to global scale, something most people don't know, and I actually didn't know this until about 2 years ago, but Azure's invested pretty heavily in enabling the largest number of regions globally. We have 50 of them. We have about 4,500 peering points that are direct peers to our network. And this enables us to have really low latency access, no matter where your engineering or data centers are within your organization, to be able to run workloads both on-prem and external using the same, for example, FlexLM licensing infrastructure. They're investing billions of dollars in the network in particular. So we're currently running cable transatlantic from the US to Europe, as an example, today, in order to enable high bandwidth, removal of bottlenecks, and low latency across these 50 regions. Pardon me. So second is security and trust. So our CEO, Satya, likes to talk a lot about trust. So trust has to do with security, but it also has to do with things like privacy and transparency. There's a number of pillars to these that I know one of my counterparts, Mushtaba, will talk to you later. I think if I can get PowerPoint to operate. There we go. There's a number of pillars when it comes to running VMs in cloud infrastructure that we treat holistically and are investing in. So it's everything from physical to network to virtual machines. All of these areas have whole teams dedicated to enabling various aspects of security on them. But the one thing I will say that is unique about Azure is that we have gone to the trouble of actually getting them certified for many of the sensitive workloads that chips tend to be deployed into. So from a regulation and compliance standpoint, we have the most number of certifications globally as well as within the US and in different industries and regions to enable sensitive workloads to operate externally on VM infrastructure. Next is high performance computing. So the pillar we talked about there was around enabling hardware that is cost performant relative to internal. So in a typical industry, there's normally burst capacity that's generally required. People always have to figure out, where do I size my cluster relative to peak versus median usage. In semiconductors, there's a slightly different take because of the license cost. So typically speaking, the problems are really around missed opportunities for re-verification or for burst workloads. How do I take and operate all of the licenses I have as cost effectively as possible over the time that I have them? The challenge on-prem infrastructure is that you buy a server and you get the same amount of compute per dollar over a 3-year period. So when you buy server infrastructure, you're actually signing up for a certain amount of compute per dollar for that server over the depreciation life cycle. Most people will depreciate it over 3 to 4 years, but actually keep it for 5. In terms of cloud, you have the opportunity of actually re-looking at that cost performance every year. So normally there's an opportunity to optimize for that really expensive license every year in a way that you can't do on-prem in a very trivial way. So what we try to do is make it very easy to take these workloads, leverage whatever VM infrastructure is required, and deal with variable demand when you have it. And so this really involves 3 parts of a total solution. The first one is actually focusing on the infrastructure itself so that we have fast, cost-optimized infrastructure that'll run at scale. And by at scale, I mean tens of thousands to hundreds of thousands of cores for individual workloads. We want to be integrated with whatever Linux and other infrastructure that you need. In fact, most of the VMs that we run in Big Compute are Linux VMs. And be able to deal with governance and cost control. Normally, it would be great to be able to leverage our Active Directory infrastructure to say this OU group gets access to this amount of compute on a cluster. A lot of the tooling that we've created enables you to do just that. All right, I'm going to go back to the keyboard here because this is working reliably. So the families of infrastructure we have, there's a number of them, everything from general processing to general purpose VMs. This has typical RAM ratios that are D&E, work really well early on in your design process. We have large memory VMs that have 4 terabytes of RAM per server. We have FPGAs available, managed disks with high performance storage, and also Cray clusters that you can add in for particular workloads. So interestingly enough, if you have a throughput workload like semiconductor design, and you want to be able to run a particular cluster design that has high clock frequency, for example, we can accommodate those kinds of requests through our partnership with Cray. And in addition, Microsoft's invested in buying both Cycle Computing for management of the compute workloads and Azure for the data layer alongside it. I think the process-wise, I always get just blinded by sheets with different VM types on them. This slide is really aimed at trying to help you navigate. We have, for whichever stage of the process you're in, there are various series of VMs that can help you execute those workloads as cost effectively as possible, as well as software tools around scheduling and resource management and data and file system to essentially support the entire front end and back end design workflows. So in terms of Azure and Cycle Cloud, I talked about this briefly. We were managing about 1/3 of a billion hours every year. That number was going up exponentially, about 7x every 2 years. We help a number of different organizations from Western Digital in the design space through insurance companies and people doing rocket design. The workloads themselves are all facing the similar challenges in time to result being a critical factor, and depending on the industry, license costs or storage IOPS or interconnect are all critical factors. Our customers span a majority of different industries, from everything from manufacturing to life sciences and financial services. Fundamentally, the software tool chain that we have helps you solve 3 problems. So getting workloads up and running. So how do I take this cluster of LSF that I have on-prem and be able to run this at scale externally in the cloud when I need to for a verification process, and then shut it down and manage my costs in the process? So that problem has, how do I deploy and manage an HPC cluster that'll scale properly and enable me to have cost guardrails and control, as well as how do I easily manage the data and compute side of that workload so that I have my data on-prem in its single namespace and be able to run that externally when I need to, and then turn it off when I don't. So all 3 of these problems, from deployment and management to the hybrid aspect, through policy and governance and putting workload guardrails around various aspects of computing and storage so that you can control cost, are all critical problems that we're aiming at. As an example, let's say you're Western Digital and you're deciding to move a large design workload. This is a semiconductor design workload that I'll talk about externally. You normally will have a design engineer or a scientist that has a large amount of on-prem infrastructure and code and software already written. So there may be a 3,000-line Perl script that no one knows exactly how it works, but it submits jobs to LSF correctly, and I'm catching chuckles in the audience, so you've been there. These kind of problems and moving them become a major issue. So the first gap that we really focus on is enabling customers to be able to move to Azure without rewriting the application. So I want to spin up the same compute environment, potentially with different infrastructure components, optimized for different parts of that workload, and templatize that so it's repeatable, manageable, supportable by the IT organization, and also manage the data and compute aspects of this. So I want to be able to take advantage of Azure as a phenomenal way to run scale-out storage in the cloud without having to bulk ship a large amount of data externally. I want to be able to leverage that as a write-through cache and give me throughput when my execute nodes are accessing it. The second component is that I want to be able to govern this. So this means controlling access, who has the ability to run this, do they have authorization to run this workload, having controls and guardrails and policies around cost, and then dealing with all of the aspects of which VMs were spun up, what versions of software were they running, so that I can meet various compliance and audit requirements, as well as do reporting on those data sets to upper management. So these are essentially the problems that we try to solve with Cycle Cloud. The workload with Western Digital that I'll highlight in particular is being able to do design simulations of the small layered semiconductor that sits on top of the head that's doing reads and writes off of the spinning platters. So they had basically a combinatorial problem. There were millions of designs. Each design took a significant amount of compute time to be able to run, and they needed to rerun this particular workload that had taken a year internally to be able to execute. They wanted to run it externally in a far more significant period of time. So we actually spun up about 70,000 cores to enable them to move their data externally, spin up the execute capacity, attach it to their internal compute, and be able to run this hybrid workload and auto-scale the resources, turn them on, turn them off, and do it in a way that optimized for cost. So we take advantage of things like temporary instances, like low prio, to be able to run the workloads. The results are that, in this particular instance, when we ran, we were able to actually evaluate this 70 years of simulation that was required for this workload. It was about 610,000 hours of compute. Got done in about 9 hours on 70,000 cores. It was a 90x faster runtime than what they had in-house. It actually enabled their engineer that works on this class of problem to be 2x as fast in terms of their productivity. So their productivity gain yielded a 2x time to market for this particular product, and essentially enabled them to store far more bits per square centimeter on that platter than would have been possible otherwise. So this is a classic example of a burst workload, one that's been running on-prem, that needs to be able to run off-prem periodically. It's an opportunity cost issue. They want to be able to run something once at large scale to be able to execute it. Now that's actually productionalized, and they run this day to day over the course of a given year. It's normally running a majority of the year, let's put it this way. So the logistics of how this works is, let's say you have a scientist or an engineer, Ben and Jen. Jen decides that she needs to be able to run a workload externally, and so within Cycle Cloud we have a UI for spinning up various workloads. An example would be a Spectrum LSF cluster to be able to run a compute job. We would actually orchestrate that cluster, be able to deal with the VMs that come up. If any of them come up in a not working state or a state where they shouldn't be in production, we have a heavy amount of automation to fix any issues that are in the infrastructure themselves, because you're essentially burning in the cluster live as you provision it. We'll then also, once the jobs are submitted into this environment, we'll deal with provisioning the right infrastructure to execute the workload at the right time, and again, do error handling, scale management, cost management as part of that process, and then ensure that data ends up at the back in the internal environment and can be processed and read and analyzed by these engineers. Once this workload's actually done, this LSF cluster template will spin down, and we actually provide a bunch of operational and optimization data as well. So we can tell you, here are all the VMs that we provisioned. They were done in the following way with the following security group so that network access was restricted. We can tell you where jobs ran the cheapest or the fastest on a given set of VM families, and also do alerting that, for example, Ben has done this twice this month and is actually approaching his budget or is above his budget as part of doing it. So all of these operational guidelines are components of what Cycle helps manage. And it's basically the goal to enable you to have a complete workflow management system for running these large-scale workloads across internal and external compute capacity. So with that, let me talk a little bit about storage. So every cloud provider offers a number of different storage options. We offer the same one. So having disk-based storage, high-performance IOP-based storage, object storage, as well as ways of importing large amounts of data through Databox. But the most interesting one in particular that I want to talk about for these workloads is the Azure hybrid storage solution around Azure. So Azure itself essentially presents an NFS and CIFS and Samba capability in front of what is a high performance write back cache. So this is basically a cache that accepts in writes and writes them directly back to your NetApp or your Isilon, but also from a practical standpoint provides very high performance reads to scale out compute clusters that are executing simulation workloads. So the critical piece of this that I think is most exciting is that they have both an on-prem appliance and a virtualized offering inside of Azure. It's going GA later this year. Public preview will start in September. That essentially enables you to be able to run workloads across that where your traditional data is sitting inside on NetApp or Isilon, and be able to run that externally inside of Azure without changing your workload at all and getting great performance. So the classic message here is that the physical FXT, which is Avir's appliance, enables you to get better performance, so you get NAS optimization on your current NAS implementation. It also enables a file system for private object storage if you have such a thing internally, and it's valuable to do that. But when you combine it with Cycle Cloud, we can essentially orchestrate the virtual compute cluster, the virtual FXTs, and allow you to tier your storage into Azure Cloud Storage. So you get a cloud-based NAS that sits in front of high-performance disks, but also can leverage our blob storage as well, and support bursting scenarios off of your internal NAS when running. So you essentially have the ability to run data that's sitting in our blob store, so it's very low cost, and put a high-performance interface in front of it, but also be able to leverage data that you already have on-prem inside of your Isilon or your NAS, your NetApp, and be able to execute that against a cloud-based compute cluster simply and easily. So these scenarios essentially allow you complete storage management of your data across a number of different possible scenarios between on-prem and Azure. And this is something that I think Azure really has a significant investment and vision around enabling hybrid. So based on this, I think we have essentially, of the three categories of infrastructure, we have complete solutions around not only Azure storage, networking, we didn't talk about a lot, but we have a significant investment in our network. We own our network. We have global VNet peering and can enable you to access compute that is local to where your FlexLM license server is, as an example. We also have management software and management tooling to enable you to be able to run those workloads at scale and manage costs and manage access within your organization, so that multiple groups with multiple users can run multiple applications simply and easily on competitive storage and compute offerings. So hopefully today I talked about most of these topics. We have the ability to do customized hardware, whether it's the H series or Cray or some of the other offerings, the M series within Azure. We have essentially a management tool to enable you to manage workloads that are burst and workloads that are dedicated on-prem, so you can route compute between on-prem or external compute capacity. We've invested in Avir to enable us to do essentially an NFS interface in front of blob storage, so we meet your applications where they are and enable high-performance file system. Cycle also enables you to manage and orchestrate LSF and grid engine-oriented clusters inside of Azure simply and easily, and essentially enable you to support running EDA workloads on the cloud. And this is what our offering is. So with that, I'll turn it over. I think I came in just under 30 minutes. I think we got about 15 minutes for questions and answers. I see a lot of familiar faces, actually. Okay, great. Thank you.